Okay, we are at section 19.8, magnetic force between uh, two parallel wires, and that's where we are. As we have seen, a magnetic force acts on a current-carrying conductor when the conductor is placed in an external magnetic field. Because a conductor carrying a current creates its own magnetic field around itself, it is easy to understand that two current-carrying wires placed close together exert magnetic forces on each other. Let's consider two long, straight, parallel wires separated by a distance d and carrying currents I1 and I2 in the same direction as shown in the figure. Wire 1 is directly above wire 2. What's the magnetic force on one wire due to the magnetic field set up by the other wire? In this calculation, we are finding the force on wire 1 due to the magnetic field of wire 2. The current I2 sets up magnetic field B2 at wire 1. The direction of B2 is perpendicular to the wire, as you can see in the figure. Let's calculate the magnitude of this magnetic field. B2 equals mu 0 I2 divided by 2 pi d. Okay, remember that the magnitude of the magnetic force on wire 1 in the presence of B2 due to I2 is this equation. Force 1 force 1 equals B2 I1 L. Okay, let's substitute our expression for B2, which here B2, if B2 is equal to mu 0 I2 over 2 pi d, then we can substitute that into the F1 equals B2 I1L equation, and you can see that F1 is equal to mu 0 I1 I2 times L, the length, divided by 2 pi d. Okay, the direction, let's see, which we can, okay, we can rewrite this here. F1 divided by L equals mu 0 I1 I2 divided by 2 pi d. The direction of F1 is downward toward wire 2, as you can determine by using the right-hand rule number 1. This calculation is completely symmetric, which means that the force F2 on wire 2 is equal to and opposite F1, as we expect from Newton's third law of action-reaction. So the bottom line here, and I'm not going to make you responsible for all these equations. I don't think I'll do any problems, but the bottom line here is that if the currents are going in the same direction, the force pulls the wires together. If the force is going in opposite directions, then the wires spread apart. So it may just be kind of a sentence question that states that. Let's see. And let me restate that. So if two current carrying wires are carrying the currents in the same direction, the force is attractive. If the currents are going in opposite direction, the forces on the wire are repulsive. They push against each other. Now let's go to some magnetic force. Some definitions. Definition of an ampere. We have shown that parallel conductors carrying currents in the same direction attract each other. You can use the same procedure to show that parallel conductors carrying currents in opposite directions repel each other. I just said that on the previous slide. The force between two parallel wires carrying a current is used to define the SI unit of current, the ampere. If two long parallel wires 1 meter apart carry the same current, and the magnetic force per unit length on each wire is 2 times 10 to the minus 7 newtons per meter, the current is defined to be 1 amp. We can now define the SI unit of charge, the coulomb, in terms of the ampere. If a conductor carries a steady current of 1 amp, the quantity of charge that flows through any cross-section in 1 second is 1 coulomb. All right, this ends this section on magnetic force between two parallel wires. The next section is section 19.9, magnetic fields of current loops and solenoids. Okay.